Neutron stars are the most extreme things, except for black holes. Since its origin in the Big Bang 13.8 billion years ago, the cosmos has unfurled a story of majesty and wonder. There's much we think we grasp, but so much more that leaves us in the dark. Our universe, simply put, is so vast that we have barely scratched the surface of what's out there. There are an estimated 400 billion stars in the Milky Way alone and more stars in the observable universe than there are grains of sand on Earth. When we dive into the fascinating world of stars, we find something that shouldn't exist, but there they are. Born from the cataclysmic death throes of massive stars, these spooky stars are some of the universe's most extreme objects. They are dense, really, really dense. They are so dense that a single teaspoonful of their material would weigh 1 billion tons on Earth. That's as much as 166 Great Pyramids of Giza. What's more fascinating, defying our theories about dead stars, those bizarre stars can live forever. Scientists call them neutron stars. NASA estimates that there are as many as 1 billion neutron stars in our Milky Way galaxy. The majority of neutron stars discovered thus far are young neutron stars that sweep energetic radiation over the Earth as they rotate at incredible speeds. Older neutron stars that have had billions of years to slow their spin and cool are less conspicuous, but are no less fascinating. As Large Area Telescope Science Team member David Thompson of NASA's Goddard Space Flight Center said, "With neutron stars, we're seeing a combination of strong gravity, powerful magnetic and electric fields, and high velocities. They are laboratories for extreme physics and conditions that we cannot reproduce here on Earth." Join us as we dig deep into secrets lurking within the densest and most mysterious objects in the universe. Think about it. In the depths of space lie dead stars, each containing more mass than the Sun, but crammed into a space the size of a city. Neutron stars are so tightly packed that a single teaspoon of their contents would weigh more than Mount Everest, or about as much as every human that has ever lived. What's more, neutron stars spin multiple times a second, are highly magnetized, and spit out rotating beams of radiation like celestial lighthouses. How do neutron stars form? Neutron stars are the remains of the cores of massive stars that have reached the end of their lives. The life of a normal star, no matter its size, is a balancing act between the inward push of gravity and the outward push provided by photons generated as they conduct nuclear fusion, the forging of heavy atomic nuclei from light nuclei at their cores. When stars run out of hydrogen to fuse into helium, they reach the end of their main sequence of nuclear fuel-burning lives. The outward energy ceases and gravity wins out, causing the core of the star to collapse in on itself. As this happens, nuclear fusion in the outer shell of the star continues, and this causes these outer layers to puff out. These shed outer layers cool around the still collapsing core, which, if it is massive enough, will begin a new round of nuclear fusion, forging helium into heavier elements like carbon. Even stars with masses between 10 and 20 times that of the Sun reach a limit to the heavy elements they can forge, usually ending up with a core of almost pure iron. Even this heavy element isn't dense enough to prevent massive cores from further collapse. As this occurs, the gravitational pressure is so intense that the negatively charged electrons and positively charged protons that comprise the iron nuclei in this stellar core are crushed together, creating a sea of uncharged or neutral neutrons. Some massive stellar cores are, at this point, saved from further collapse by a quantum phenomenon called neutron degeneracy pressure, which occurs when such a density is reached that neutrons can no longer be packed any closer together, leaving them as neutron stars. What's notable is that a neutron star is 90% neutrons. Effectively, each one is a giant, city-sized atomic nucleus. A neutron star has a similar structure to our planet, with an atmosphere, crust, and core, but what goes on inside is very different. The gravity of the neutron star maintains an atmosphere of hydrogen, helium, and carbon heated to around 2 million degrees Celsius. It's just a few thousandths of a millimeter thick. The outer crust is made of a mixture of electrons and atoms that have had some or all of their electrons removed, known as ions. Here, you will find superconducting protons. A superconducting material offers no resistance to electrical current, and so the current can flow through it without losing any energy. The least understood part of a neutron star, the inner core, could be made of a soup of quarks, the particles that make up protons and neutrons. The neutron star's magnetic field holds a lot of sway in this region. It could help fragment the crust and generate starquakes. Material in the inner crust takes the form of electrons, neutrons, and atomic nuclei. Neutron stars exist in space because of a delicate balance of forces. On one hand, you have gravity trying to collapse the star. Research published in July 2021 found that the gravity of neutron stars is so extreme that mountains on their surface can barely reach a millimeter in height. But resistance to gravitational collapse comes in the form of something called degeneracy pressure. This is generated because there comes a point when it is too hard to squash nuclear material closer together, and so the two opposing forces balance each other out. This means that the most massive neutron stars should also be the smallest. More mass means stronger gravity and therefore a more compact, tightly squeezed object. At least, that is how it is supposed to work. Imagine the surprise for astronomers when, in 2019, they stumbled across a seemingly impossible neutron star. This neutron star currently makes no sense, a neutron star that has a density far greater than its vast size should allow. Explaining its existence wouldn't just answer important questions about neutron stars that we've been asking for decades. It could also tell us more about nuclear physics and gravity, to boot. The neutron star in question is called J0740 and sits 3,600 light-years away in the constellation of Camelopardalis, the giraffe. Like many stars, it exists in a pair or binary star system. Its partner, 662 Yarrow, is a white dwarf, another type of dead star. According to Anna Watts from the University of Amsterdam, who is part of a team that's been studying J0740 and other neutron stars, as these objects spin, their brightness changes because there are hotspot regions on their surfaces. We can use this characteristic to build up maps of those surfaces. To accurately chart the surface detail of an object the size of London from a distance of over 3,600 light-years, or 34 quadrillion kilometers, is quite a feat. Some feat, it takes 3 to 4 weeks of observations over the course of a year. These surface maps are one of the tools Watts and her colleagues use to estimate the mass and size, radius, of neutron stars, such as J0740. It turns out that J0740 is the most massive neutron star we've ever found, tipping the scales at 2.1 times the mass of the Sun, so it should also have the smallest radius, except it doesn't. It's just as wide as another neutron star with only 2/3 as much mass. That means the material inside J0740 isn't as compressible or squishy as astronomers tend to refer to it as they thought. That potentially gives us clues about what's going on inside the core, which is important because, of all the layers a neutron star has, the core is the least understood. Why form a neutron star and not a black hole? Back to the formation of neutron stars. If this process of neutron star birth sounds familiar, that could be because it is also the path that a massive star takes to become a black hole. The question is, why do some stars birth neutron stars while others leave behind black holes? The key difference seems to be the collapsing stellar core possessing enough mass to exceed the protection that neutron degeneracy offers. Currently, scientists aren't exactly sure where the delineating line between black holes and neutron stars lies. This uncertainty exists because the physics inside neutron stars remains difficult to investigate. The heaviest known neutron star has a mass equivalent to around 2.5 times the mass of the Sun, while the lightest known black hole has a mass of around 5 times that of the Sun. Thus, there is a mass gap between these two types of dead stars, which scientists are currently attempting to narrow. It is in this gap that the line between one path and the other must lie. Researchers currently think that the dividing line between neutron stars and black holes lies much closer to 3 times the mass of the Sun than 5 times the mass of the Sun. As the main difference between a black hole and a neutron star is mass, it only makes sense that neutron stars accumulating material from a binary partner could eventually become a black hole. The process of mass accumulation could take as long as millions of years, but the eventual transformation from a neutron star to a black hole takes less than a second. Will the Sun become a neutron star or a black hole? While the line between neutron stars and black holes is vague and poorly defined, the line between the stellar remnant that our Sun will become, a white dwarf, and a neutron star is much better understood. When the Sun reaches the end of its hydrogen supply in around 5 billion years, and the outward pressure protecting against gravitational collapse ceases, its core will collapse. After passing through a red giant phase during which the Sun's outer layers will swell out and swallow the inner planets, including Earth, the Sun's core is left as a smoldering white dwarf. Just as neutron stars are prevented from becoming black holes by neutron degeneracy pressure, white dwarf stars are protected from further collapse by electron degeneracy pressure, which stops electrons from being crammed any closer together. Electron degeneracy pressure is much weaker than its neutron equivalent, and astrophysicists also have a better idea of the masses needed to overcome it than they do for neutron degeneracy pressure. To eventually become a neutron star, this white dwarf would have to exceed what is known as the Chandrasekhar limit, which is generally considered to be 1.4 solar masses. According to the SAO Encyclopedia of Astronomy, that means that the core of the Sun alone would have to have 1.4 times the total mass of the Sun. The Chandrasekhar limit mass, first predicted by Subrahmanyan Chandrasekhar in 1931, has so far corresponded well with observations of white dwarfs, as we are yet to find a stellar remnant of this type with a mass above 1.4 solar masses. NASA estimates that the Sun would have to be 10 times more massive to end its life as a neutron star, or it would have to be 20 times more massive to leave behind a black hole. In what remains of the solar system in 5 billion years or so, the size and mass of neutron stars are dramatic. To consider how violent the near-complete gravitational collapse that births a neutron star is, one only has to look at the material it creates and the dimensions of the object it comprises. The collapse of massive stellar cores results in an object that has from 1 to 2 times the mass of the Sun, but only a width of between 6 and 12 miles. Imagine the Sun reduced in size until it is a sphere that sits comfortably within the city of New York, which is 35 miles wide. Being reduced from a diameter of 870,000 miles to just 12 miles would have a striking effect on the material within it, and this is definitely the case for neutron stars. NASA estimates that a single sugar cube comprised of this neutron-rich matter would weigh around 1 trillion kg or 1 billion tons if it were brought to Earth. That's a sugar cube that weighs as much as 3,000 Empire State Buildings, or the entire human race. This makes neutron star matter the densest material we can see in the universe, and this has another effect. Neutron stars are so dense that the speed it would take to escape their gravitational influence is half the speed of light. As a consequence, the gravity of neutron stars is so strong that NASA's Goddard Flight Center says if a marshmallow were dropped to the surface of one of these exotic stellar remnants, it would accelerate so quickly that when it struck the surface, it would release energy equivalent to the detonation of 1,000 hydrogen bombs. While marshmallows don't tend to rain on neutron stars, gas stripped from companion stars in binary partnerships with these extreme stellar remnants often does. When this gas hits the neutron star's surface at speeds as great as millions of miles an hour, it creates powerful firework displays in X-ray light that flicker in intensity thousands of times per second, or perhaps burst only once every few years. The density and gravity of neutron stars aren't the only things that make them the most exotic objects in the universe. They also have some other extreme characteristics. When neutron stars are born, the conservation of angular momentum results in them spinning at incredibly rapid speeds. To consider why this is the case, think of an ice skater in a spin. As they draw their arms in, the skater's rotational speed increases. A similar thing happens when the diameter of a stellar core shrinks as it undergoes gravitational collapse. The resultant young neutron star spins faster and faster, reaching speeds as great as 60 rotations per second, according to Swinburne Center for Astrophysics and Supercomputing. Many neutron stars slow as they age, reducing to rotations of around 8 times per second. But the situation is different for neutron stars that are stealing stellar material from a binary partner. This material carries with it angular momentum, and thus this transfer of matter can actually speed up or spin up the rotation of neutron stars. This can result in some neutron stars rotating as fast as 600 or 700 times per second. The fastest spinning neutron star on record, discovered in 2006 according to the National Radio Astronomy Observatory, NRAO, is PSR J1748-2446 AD, found in a globular cluster of stars located around 28,000 light-years from Earth. This neutron star spins around 716 times per second, or at 716 Hz, which is faster than the blade of a kitchen blender. Neutron stars like PSRJ 1748-2446 are discovered because, as they spin, they radiate beams of radiation from each pole, including radio, visible, X-ray, and gamma-ray wavelengths. As a result, when they turn toward Earth, these beams of radiation flash over our planet, making these neutron stars almost like cosmic lighthouses, though they are more formally known as pulsars. All pulsars are neutron stars, but not all neutron stars are pulsars. Scientists believe that the beams of radiation of pulsars are created when the powerful magnetic fields of neutron stars channel matter to their magnetic poles. These magnetic fields for some neutron stars can be extraordinary themselves. When a star collapses, it isn't just its mass that is condensed, but the magnetic field of that star is compressed as well. Magnetic fields are represented by curved lines, or field lines, passing through an object. The closer together these lines are, the stronger a magnetic field is. The collapse of a stellar core to create a neutron star pushes together these field lines. The European Space Agency says that some neutron stars can have magnetic fields as strong as 100,000 million Tesla, which is not only thousands of times more powerful than the magnetic field of ordinary neutron stars, but it is 1,000 trillion times stronger than the magnetosphere of Earth and equivalent to 100 trillion refrigerator magnets. This makes the magnetic field of magnetars some of the most intense magnetic fields in the known universe, and these fields are so strong. Intense, they can drive the surface temperature of a magnetar to over 18 million degrees Fahrenheit or 10 million degrees Celsius. With all these extreme and record-breaking characteristics, imagine what happens when two of these extreme stellar remnants come together. What happens when two neutron stars collide? Neutron stars can exist in isolation, only detectable by their surface temperature, or they can dwell in partnerships with ordinary stars, often siphoning off their material. In some cases, they can exist in binary systems with another neutron star. In these circumstances, according to Einstein's theory of general relativity, as these binary neutron stars orbit each other, they create ripples in spacetime called gravitational waves. Just like material falling to the surface of a neutron star grants it angular momentum, as gravitational waves ripple away from binary neutron stars, they carry angular momentum out of the system. Loss of angular momentum causes the neutron stars to draw close together, and as this happens, they radiate gravitational waves even more strongly, increasing the rate at which angular momentum is lost. Eventually, this causes the neutron stars to collide and merge to create an even larger neutron star. The violent event, an explosion known as a kilonova, which after as long as 1 billion years of prelude with the stellar remnants dancing around each other, lasts just a few milliseconds. Kilonovas release energy equivalent to millions of times that of the Sun, sending out an intense burst of space-distorting gravitational waves and a short but powerful burst of gamma rays. They can be responsible for forging heavy elements like gold, silver, and platinum. Depending on the size of the neutron stars that go into this kilonova event, the result could be a hypermassive neutron star that is too tremendously huge to remain stable thanks to neutron degeneracy pressure, and thus rapidly collapses in under a second to birth a black hole. Neutron star mergers produce gold. In 2017, astronomers observed for the first time gravitational waves, ripples in the very fabric of spacetime, and light that was sent radiating outwards from a collision between neutron stars. This one neutron star merger, occurring in a galaxy just 130 million light-years away, and just the 8th gravitational wave event ever observed, seemed to provide the answer. A wide variety of heavy elements were created in this merger and detected in its afterglow, including so much gold that if we were to place it on a scale, it would weigh about 20 times as much as Earth's moon. Thus, when the event was announced to the world, it was accompanied by a now-famous video where the executive director of LIGO, Dr. David Reitze, pulled out his great-grandfather's gold watch, an artifact that's now more than a century old itself, and declared that the gold in this watch was very likely produced in the collision of two neutron stars approximately billions of years ago. But then a funny thing happened. Over the next few years, bringing us up to the present day, only one other neutron star merger has ever been detected, and unlike the first event, it did not produce a kilonova or create any heavy elements. Despite several years of additional observing time, significant upgrades to the existing detectors that increased their sensitivity range, and tremendous numbers of black hole mergers and many black hole neutron star mergers subsequently observed, bringing the total number of gravitational wave events up to over 100. That one event from August 17, 2017, remains the only directly observed neutron star merger to produce heavy elements. This has taught us something remarkable and important. Our initial estimate that around 100% of the heaviest elements in the universe were produced from neutron star mergers is no longer consistent with the data we've collected. Something else, beyond what we've seen so far, must be at play. Three possible explanations immediately spring to mind, but all three have complicated problems. Perhaps the neutron star merger rate creating kilonovas was greater in the past than it is today. Perhaps the brightest, most energetic supernovae create a larger abundance of heavier elements than expected, and these play an important role even for elements heavier than zirconium. Or perhaps, during the giant phase of an evolved star's life, a slow addition of neutrons allows elements to build their way up the periodic table, creating those observed heavy elements. However, each scenario, compelling as it is, has its flaws. There must be something else at play beyond what is known today. So, the most responsible stance to take scientifically is to state that we don't know and must collect the critical data if we hope to find out. What happens when a neutron star collides with a black hole? In a world-shattering revelation, astronomers announced last month that they may have detected a collision between a neutron star and a lightweight mystery object, an object larger than the largest known neutron star but smaller than the smallest known black hole. The finding sheds light on objects that exist in this murky realm, which was long thought to be empty but in recent times has revealed otherwise. More specifically, a signal detected in a pocket of the universe roughly 650 million light-years from Earth indicates a rare merger between a neutron star and what astronomers suspect is a surprisingly lightweight black hole. The pair would have danced around one another and merged about 650 million years ago, generating ripples in the fabric of space and time known as gravitational waves. These waves were sensed and flagged on May 29, 2023, by a network of antennas in Japan, Italy, and the U.S. associated with the LIGO-Virgo-Cagra collaboration, or LVK for short. According to Evan Getz, a LIGO researcher at the University of British Columbia in Canada, these are rare events. It's very exciting for the community to study as the first one of its type. The black hole candidate, which is about 2.5 to 4.5 times heavier than our Sun, is heavier than the established limit of 2.5 suns for a neutron star but lighter than the lightest known black hole, which weighs about 5 solar masses. This places the newfound object within the mass gap, a mysterious region that separates the heaviest neutron stars from the lightest black holes. This discovery, as Michael Zevin, an astrophysicist at the Adler Planetarium, said, hints at this mass gap being less empty than astronomers previously thought. Black holes, small and big, are born from the violent deaths of immensely massive stars. A few models of how stars evolve, however, predict black holes with masses within the mass gap range cannot directly form from such stellar deaths. In Zevin's words, it does appear that it could be possible now with these observations. Perhaps astronomers need to tweak the models, or maybe we really do have a more complicated evolution of a heavy neutron star that evolved into a black hole. It's hard to know just from this one example. In early 2020, astronomers announced the first conclusive detection of gravitational waves created by a collision, which involved a stellar remnant right in the mass gap range. However, the discovery team couldn't classify the object with conviction at the time, concluding it could be either the biggest known neutron star or the smallest known black hole. As for the latest finding, astronomers say they cannot pinpoint just where in the sky the mammoth objects merged because only one LVK detector was recording data when the signal was detected. Nevertheless, the finding has raised hopes that there may be many more such mass gap objects out there waiting to be discovered. As Heather Fong, a LIGO researcher at the University of British Columbia, said, there is a lot more potentially we could find and a lot more to look forward to. After a short maintenance break, LVK detectors resumed measuring ripples in spacetime on April 10. The LIGO team anticipates observing over 200 gravitational wave signals by February 2025, including hints of a few objects within the elusive mass gap range. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode. Subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.